Hi, this is David. I am a solution architect with Microsoft. Just passed my 10-year anniversary with this company, and I am here today to talk to you about a tool that I only recently learned about, maybe in the last year or so. It's called Azure Data Explorer. This is a data store that has an associated query language called Kusto Query Language. So these are sometimes abbreviated as ADX and KQL. You may hear me saying something like that. This is me. As I said, I'm a partner solution architect. You can find me online at my blog, davidgiard.com, or at one of these two television shows that I produce. One is called technologyandfriends.com, and I interview smart people about topics of interest to technologists. And the other one, aka.ms/gcast, is short screencasts of some technology that hopefully you'll find useful. All right, this is what we're going to talk about. Azure Data Explorer. What is it? When should you use it? What are the use cases? How do you use it? How do we create things like clusters and databases and tables and other artifacts within this data store? And then how do we use the commands to manipulate those things? Next, we'll talk about Kusto Query Language, or KQL. I'll show you the basics of that. It's kind of similar to SQL, if you're familiar with that. And it's a way of analyzing time series data and other types of data as well, but really time series data is what it's optimized for. I'll also show you how to do some geo functions using KQL, which is something we used on our last project. And then I'll talk about how to optimize using things like materialized views. Let's get to it. What is ADX? It is a massive data store. When I say massive, I mean petabytes of data. So if you want to store extremely large amounts of data and you want to be able to access that data in near real time, this is a good solution to start looking at. It works with structured data, semi-structured data, or unstructured data. So there is some schema involved in it, so I wouldn't quite call it a NoSQL database. However, there's a lot of flexibility, and there's nothing enforced like referential integrity, deleting child records or preventing the deletion of child records if there's a parent record and so on. I think I said that backwards. Preventing the deletion of parents and orphaning the child records. Things like that. It doesn't have that enforcement, and as a result, it actually is really, really fast because it's up to you as the developer to store data. It is extremely scalable, not only in the manner of storing lots and lots of data, petabytes of data, but also in terms of usage. It's all deployed on Azure, and Azure has the capability of being reliable and scalable. It can scale out to multiple nodes. It is the managed service within Azure, so it frees you from the responsibility of maintaining that database. You don't have to hire a DBA to tweak that or to replace the hardware or to optimize the infrastructure underneath. You can focus on your data, your application, and the business problem that you were trying to solve. This is a good flowchart, how to use or when to use ADX, what it's good for. I copied it from this URL down here at the bottom. And it was, the whole idea is that if you want lots of data and it's structured or semi-structured, then this is a really good tool for you. If you want to be able to access it fast and near real time, one of the good use cases for this is IoT data. IoT tends to be lots and lots of data sent, sometimes multiple times per second, and we're storing this and you want to access it near real time. ADX is a great solution for that. Now, if you want things like enforced referential integrity, probably not for you. Probably want to do something more traditional relational database like SQL Server or Oracle. If you want some of the other tools involved like data warehousing or SQL pools or ETL tools, it doesn't come bundled with that. All those bells and whistles that you get in a tool like SQL Server, they're not bundled with ADX. So if you want that kind of extra features, that's great. Go use something else. But if you want highly scalable, highly fast, massive storage, then ADX is something worth looking at. One of the reasons it is so fast is it doesn't have all those extra features. It's only been about a couple of years since this has been released publicly, but it's older than that. ADX has been used internally by Microsoft for things like logging Azure SQL database or the telemetry in Microsoft Office. If that pop-up comes up in Word and says, "Do you want to make the product better? Click here." And if you say yes, it'll send usage information back to Microsoft, and we can analyze what features are being used and how they're being used. Well, that's all stored in ADX. It's used for Azure Monitor. It's used for Azure Application Insights. These are internal tools Microsoft has been using it for, and as a result, over the years that they've been testing it, it's been banged on. So the product is pretty darn stable. It was even in its 1.0 general release, because it had been used internally by these tools that are really storing huge amounts of data. You think about all the people that are using Microsoft Office, all the people that are turning on Azure Monitor, and how much data that has to store. These have been pretty good tests by internal teams for this. A lot of customers using ADX. I created this slide over a year ago, but it was some of these are big companies that are using it. It's out in general release. It's pretty popular. Let's talk about the structure of how ADX works. It starts with a cluster. When you go into Azure, which I'll show you later on, there you can create a cluster, and within that cluster you can create multiple databases. Within each database you can create multiple tables, or multiple functions, or multiple views for those tables. If this looks familiar, maybe it's because you're using a tool like SQL Server or Oracle, which has a really similar structure to this, where things are stored logically in a database and there are tables below that. Here's a screenshot. Again, I'm going to show you this in real time, but just how easy it is within the Azure portal to create a new cluster. You just select a resource group, you give it a name, you tell it what region to be in, and you can specify the workload. The more powerful machines, of course, they cost more money, but if you don't need that, you can select a less powerful machine. So it's up to you to scale this up according to your workload needs. Once you have a cluster, within that you can then create a database. This is even simpler. You give it a name. There's a retention period. By default, that's 365 days, but you can change that or turn it off entirely. That's at that point you probably want to have some archive strategy that says move this somewhere else in 365 days rather than keeping this huge amount of data in hot storage. Also, there's a caching period as well, where data is kept in memory. So if you find that for the first couple of weeks you really want extra fast data, maybe you care less about that for historical reporting, you can set this caching period to say how often, how long items remain in cache for fast retrieval. And then creating a table, also very simple here. Once you create it, you can provide a schema. There are actually command line tools for doing this as well. So here's the command line tools: create table, create merge table. The difference between those two is create table. Actually, it's create table. It will fail if the table already exists, whereas create merge table will not fail if the table already exists. There's things like dropping a table, altering a column, renaming a column. Over here on the right, there's a sample syntax for creating a table called customers with these 6 fields in it. And you can see it supports data types for these. So there's a little bit of schema. Again, I won't call it a NoSQL database, but it is a lot faster than a traditional relational database. All right, ingesting data. There are multiple ways that you can get data into ADX. You can, for example, pull it in from Azure Storage. You can write a query to pull it in from another ADX table. You can do streaming ingestion. For example, if you have subscribed to an event hub and have that data coming into ADX, or you can write code to ingest inline. And so, for example, for this demonstration, I wanted to get some sample data, and I added something like this: .ingest inline into table customers, and just explicitly listed a dozen customers or so. All right, that's enough of the slides for now. Let's switch over to a demo. It's now time for a demo. I am going to log into my Azure portal right here. And the way I create just about anything in the portal is with create a resource, that big plus button. I can search for ADX in here. There it is, Azure Data Explorer, create Azure Data Explorer. Click on that. And then I want to create a resource group. I can select an existing one if I want to, but I'm going to call this one DG test. I always name everything that's for demo DG test so I know how to find it and delete it. And I'll call this FT for Festic Tech and then RG for resource group. How about that? There's my new resource group. The cluster name, I'll call it DG test FT ADX. I'm going to put it in the East US because I'm located in the US. And then selecting a workload. Here, there's things that are optimized for IO and optimized for compute. Or you can just use dev test, which is by far the cheapest ones here. It only gives you small cores. But if you select one of these other ones, you can actually specify how large of a machine that you want here or for that one. Same thing here. Well, dev test is good enough for these demo purposes. That's fine. I'll just take the default availability zone. So I have some fault tolerance on that. I could put other things in here, specifying the scale and auto scaling. These aren't available in the dev test, but other configurations on here, supporting streaming ingestion and purging and auto stop cluster. That one's kind of nice because it does get kind of expensive if you let this run all the time. Some security. I don't really, for this purposes, I don't really need all that. I'm just going to click on review and create, which brings me to this review and create tab, does some validations, make sure there's nothing inconsistent on here or missing. And then I click on create to create my cluster. And that's going to take a little bit of time. So I'm going to pause the video right now and come back to it when the deployment of my ADX cluster is complete. This is now done. It took about 10 minutes for the cluster to get deployed on Azure. If I click on Go to Resources, then I can see the resource right here and set some properties like permissions, who can access it, and so on. Now that we have a cluster, let's create a database. Down here, we can select the databases blade. Of course, there are none. We just created this, but we can click this button or this button to add a new database. And this is the screenshot that I took from my slide. I'm going to call this one the same as before, DG test FXDB for database, or FT rather, FTDB for database. Retention period, I'll say 3. I'll just take the default for that. That's fine. Cache period, 31 days default for that. That makes sense. And I'll click on create. This takes a lot less time. It will create a database. And there it's done. And now I have a database right here. Now that we have a database, we can start creating objects inside of that database. Objects like, for example, a table or a view or something like that, and populating those. For that, we're going to use the command line. So if we click over here, this is what comes up after the database is created. It's the details about the database, and there's a blade for query right here. And in here, I can put some ADX commands and some KQL commands. So the first thing I want to do is I'm going to create a table called drone data. Imagine we have drones that we've deployed and we want to just track where they are. So we want an ID for the drone. We want a timestamp, a longitude and latitude to track the location, and we'll also track the battery life. And you can see that these things have data types associated with each column. So I'll click on run, and that will create a table. And once I do that, I can query the table just by typing the name of it here, drone data, and click run right here. There's no data in there right now, but I'm going to ingest some data into this. And I'll do that using the .ingest command. So .ingest inline into table drone data, and here's the 20 or so rows that I want to insert. Each one has a date timestamp. It has there's an ID. There's a drone 1 and a drone 2, date time, a longitude, a latitude, and the battery life, which seems to be dwindling over time just slowly. So let me run this thing here. Just click anywhere inside there and click run, and now it's done. And now if I query this again, you see now I have a bunch of data here. 26 records in here is what I have. All right, let me get rid of that, and I'm going to create another table. This one I'm going to call customers. So customers in the table, and there's the columns. A full name of the customer, the last order date, their year-to-date sales, year-to-date expenses, the city they live in, and their postal code. Let me just run that. And just customers right here. Shift Enter, by the way, is a shortcut for clicking the run button. So I'll do that. There's no data in here at all. Of course not. I just created that. So let me do the same thing again. I'm going to do an ingest inline. .ingest inline. And here are my customers: Bill Gates, Steve Ballmer, Satya, Steve Jobs, Larry, Jeff, Tim, Steve, Scott, and me, because it's my presentation. Okay. Let's run that, populate that data, and now when I query the entire customer tables, you see there's all the 10 records that I have in here, each one having last order date, sales, expenses, city, and postal code. All right, so now I've got some data set up in here. I've created a cluster, I've created a database, I've created some tables inside of there. That's enough for now. Let's talk a little bit about the query language. I showed you a little bit of it here. Customers is actually KQL, just the name of the table with no filter, no order by, no aggregation, nothing. But we're going to go into a little bit more detail now. As promised, now we're going to talk about the language associated with ADX. That is the Kusto Query Language, often abbreviated as KQL. And if you're wondering why there is a picture of a diver on many of these slides, it's because the Kusto Query Language was named after Jacques Cousteau, the famous ocean explorer. And it's deliberately misspelled to make it easier to find using your favorite search engine. So Kusto Query Language, tip of the hat to explorer Jacques. What's KQL? KQL is a query language, very, very fast. It is ideal for time series data because ADX, as it's written, is optimized for time series data, but you can use it for any kind of data if you want to. It will filter on it, so that's where the best indexes are. It has dozens of built-in functions that you can take advantage of, and also it's a read-only language. There isn't any way to go back to use this language to go back and update existing records or to insert rows. You need to use one of the ingestion methods I mentioned earlier if you want to insert data into an ADX database. This is strictly for reading data. And that's one of the reasons it is so fast, is because Kusto is optimized for reading data. It doesn't have to go back and check and find rows and update them. All right, here's a quick, simple example of it. If you've worked with SQL in the past, you should at least be able to read this because it does have some elements of SQL in here. In this case, there's the name of the table, telemetry data. There's a filter statement, in this case, where fleet ID equals FL1. And then there's a sorting statement below that. Order by timestamp ascending. And then these are the fields that it's going to output: timestamp, fleet ID, vehicle ID, current lat, current long. And then in this case, we have a take. So in this case, we're doing a top 100, a top N query. You need to have an order by for the take to make any sense. But if you're these are the ones at the top when we're ordered by timestamp ascending. So those would be the earliest records that match this filter criteria. All those things should look familiar to an SQL. Syntax is a little bit different, so writing it may take a bit to learn, but there's IntelliSense that'll help with that. It also has something in common with Bash language in that this pipe character means that we take the output of whatever is before the pipe, and that becomes the input of whatever is after it. So telemetry data is the entire table, and we take that as our input to this filter clause. And once we filtered it, that filtered data, then we sort it because the output of this filter becomes the input of the order by. And once we do that, we say we only want these columns here. And then once we have that, then we do the take 100. So sometimes the order is important that we execute these in because we need to think about what's going to be the input that's done first. For time series data, I mentioned that it's really good for that, and one of the reasons is that it has a few built-in functions that make it really nice when working with time series data. The prev and the next function will retrieve a previous row or the next row. So when you're ordering data and you want to know the difference between this row and the last row, let's say you order it by time series, by the timestamp, and you want to say, okay, how much did this value of this field increase between records? That's kind of a hard thing to do using SQL. With KQL, you can use the pre function to do that, or you can look ahead to using the next function and find deltas between different rows, which is really nice. The other thing you could do is summarize by bin. I'm going to show you what that means. If you've used SQL, you've probably done some aggregation, but usually you have to aggregate by a column, maybe by day or by state or something like that. Here you can aggregate by hour or minute, by some time series. I'll show you how to do that. Here it is. So here's an example of it. What we've got here is telemetry data is the name of our table, and I'm filtering it first on where the timestamp is between these two date times. And now here, summarize is how we do aggregation in KQL. And what we're going to do is we're going to summarize by bin of timestamp, comma 1 hour. That means that we're going to look at this column called timestamp, and we want only one row per hour. So this might be IoT data where we're putting, every second we're pushing information about the location of a vehicle by second. Well, maybe we don't want that many. How many seconds are there in an hour? 60 times 60 times 60. That's a lot of seconds in an hour. Maybe we want only one row per hour. And that's what this summarized by bin of timestamp, comma 1 hour means. You can change that to 2 hours or 1 day, whatever you want. And what's nice about this, so this actually raises the question. So okay, I only want one row per hour. Which row do I want? There are thousands of rows per hour if I'm sending out one per second. And the answer is we use one of these aggregation functions. In this case, argmax. We want to do the maximum timestamp. KQL ships with some geo functions, some geography functions, and we used this quite a little bit in a project I did last year. We were tracking vehicle movements, and we wanted to know things like how far a vehicle had moved in a given time. We want to know whether or not the vehicle was inside a particular area at a given time, and there's some functions that help us do that. Geo distance 2 points does what you probably could figure out. It measures the distance between 2 points. You pass in latitude, longitude of point 1 and latitude, longitude of point 2, and it'll tell you the distance between those 2 points. GeoPoint and polygon returns a Boolean, true or false, depending on whether or not a point is inside of a given polygon. You pass in a latitude and longitude and a polygon object, and it returns true if that point is inside the polygon, false if it's not. GeoPoint to S2 cell converts from a latitude longitude into something called an S2 cell value, and I'm going to talk about that a little bit later and why that's important. But here's this code right here is how you can use KQL to create a polygon object. I'll just leave it here. I'll share these slides later on, but essentially that polygon variable down at the bottom here creates a polygon object with these 4 points. So it happens to be a 4-cornered object. And what we can do is we can use that object, we can pass it into the GeoPoint in polygon function along with a longitude and latitude. That will return a true or a false depending on whether the point is in the polygon. So in this query right here, we're querying telemetry data. We want to know everything that is between this time and that time, but also only those points that are inside of a polygon. Maybe we want to know, did a vehicle make it back to the parking lot, or was it in a city during that time, or at its destination where it's supposed to be, something like that. That might be useful information to say, okay, during this time period, did this vehicle cross the polygon at all, and if so, at what times did it do so? And that's what this does. There's the output of it here. Before I'm going to talk a little bit about optimizing, but first I want to talk about functions. Functions are a little bit like stored procedures in SQL Server. They are reusable code. You can pass arguments to them. Here's a sample function, and here are the important pieces of it. To create a function, we use this command, .create or alter function. You can just say .create function, but that'll fail if the function exists. I prefer to use this. It has some properties. Right here we've got a description. Docstring is a description of it, of the function. Folder, if you want to organize them. If you have a lot of functions, it might make sense to organize them into folders. There's the name of the function. This one happens to be called device path. These are the arguments to the function, and each argument has a data type. And you'll notice that this last argument, time bin length, is optional. The reason how we know it's optional is it has a default value. So if you decide not to pass that argument, it will assume a time bin length of 1 hour. Here's the code itself for the function. This one just queries a table called telemetry data, filters by start date time and device ID. It does some arguments. It does some summarization by bin. This time bin length is, you can override that, but if you don't, it'll be by hour, 1 row per hour, and it'll take the argmax. We saw something like that in an earlier slide. Sort it by the timestamp and output these 3 columns. And when we call it, remember the name of the function was device path. We call it just by specifying the name of the function, parentheses, and then a list of values to pass into the arguments. Here I have omitted the 4th argument, the 1 hour. I could pass that if I wanted to. I could say 2 hours or 1 day or whatever. But because I omitted, assumed an hour and an output 1 row per hour. All right, here's a function that actually uses this geopoint in Polygon built-in function. Here's my custom function. I've called it devices in Polygon, and it uses this geopoint in Polygon. So if we look at this, this says show me all of the data points between the start and end time for a given fleet that are in this polygon. I want to know for all the vehicles in my fleet, how many of them passed inside this, which ones passed inside this parking lot. And show me the data points, but only showing me 1 data point per hour. And this works. This works pretty well right there. But it has some issues. One thing, it's very slow because this geopoint in Polygon is, we can't really, it's running a function on each row. So it has to do a table scan. Once it gets the timestamp, it's going to do a table scan of all the results. So first it'll filter on the timestamp, and then it's going to filter on do a table scan on those results of what's in the time scan. That could be really large. There could be gazillion rows of data points in that time span, and we're only interested in a small subset of those. So that might be really inefficient. One way we can address that is through materialized views. And a materialized view it's a little bit like a view in SQL Server. It does pre-aggregation. So whenever you insert a row into a table, then it automatically updates the materialized view very quickly. And so this data, this pre-aggregated data, is available to you later on. The way we create a materialized view is with the .create async materialized view. You don't have to use the async word, but if it's a large table, you may be waiting a long time. And we have some options here. Backfill equals true says if we say true to that, that means that it's going to for a table that has data in it, it'll create a view that includes all of the data that's already in there. If you say backfill equals false, it will only create a view of data going forward that's added later on. All right, and then in this view here, we've got we're summarizing by timestamp every hour, 1 row per hour, and we just want the argmax. So we're doing a summarization here by the bin of 1 hour ahead of time, and we're storing that in a materialized view that we're calling telemetry data underscore 1 hour bin. And so if you find yourself often querying by this, summarizing by this, it might make sense to create a materialized view ahead of time, and instead of querying the table itself, just query that materialized view, which is what I've done here. Here, instead of querying the telemetry data table, I'm querying this materialized view, which already has some pre-aggregation in here. So this can make things go a lot faster because we've already done that aggregation before we run our query. So that's one way to optimize. Another way we found to optimize for geographic data is by using a concept called S2 cells. You can learn more about S2 cells at this link down here, s2geometry.io. I took this image from that page, and essentially what S2 cells do is that it divides the Earth into rectangles of approximately equal size. I know these don't look like rectangles because they're curved, but that's only because the Earth is curved, and this is a flat projection of the Earth. But these are rectangles, and with S2 cells, we have the concept of levels of S2 cells. I think there are 30 different levels. Level 0 divides the Earth up into 6 rectangles of approximate equal size. Level 30 divides it up into gazillions. I don't know, 10 to the power of something large. It's only a few millimeters across, whereas the level 0, these rectangles are many miles across. And each rectangle for a given level is approximately the same size. So here's level 0, there's level 1, level 2, level 3, level 4, and as we get smaller and smaller, depends on the precision you want to get, is what level you want to consider for your S2 cells. All right, so there is a function, I showed it on an earlier slide, but I didn't talk much about it. There's a function called geopoint to S2 cell, and it takes a longitude and latitude of a point, and then the level of S2 cells. So this one happens to be level 9. I've done it for various levels here, 9 through 21, and I'll project all of those out here. And so these are the results here. And you can see down here that at level 9, these are pretty big cells. So everything in this latitude, longitude is in the same S2 cell, level 9 S2 cell, because they have the same value. You can tell that. When I get to level 12, looks like those are also the same. Level 15, those cells get a little smaller, and now we start to see, here's 2 of them that are in the same S2 cell at level 15. There's one, there's one, there's one. This one looks like it's in the same S2 cell as that one. So it's kind of moving out of the cell and back into it. So anything that has the same value is in the same level 15 S2 cell. That's the idea behind that. And then at level 21, looks like every one of these is a different S2 cell, or just about everyone anyway. All right, so that's the idea behind this, is we can convert these into S2 cell to get an approximation of which points are close to each other. And how can we use this to increase performance? Well, this is what we did. If we had, imagine that you have a set of data points that are just vehicles moving around the country, and there are lots of them, and you want to know how many are in this polygon. And we could do the query we did before. We did geopointed polygon and return true. But as I said, it'll have to do a table scan. And that's not a big deal if you just have a few data points. But what if you had, millions of data points? Let's say your time span was for a month, and this vehicle was traveling all over the country, and you only cared about a small percentage of those data points. Well, doing a table scan on that is going to take a really long time. Wouldn't it be nice if we could filter that a little bit further? And we can filter a little bit further by overlaying with this polygon a set of S2 cells that just covers it. The minimum number of S2 cells at a given level that'll just cover that polygon. And if we can filter based on that first, now we don't have a gazillion records to deal with. We only have a few more records than we're concerned with. So this table scan of this, it will go much faster to get that polygon, to get the vehicles in the polygon. How can we do that? Here we go. First thing we would do is to create a materialized view and add a geopoint to S2 cell. So we're going to pre-calculate these S2 cells. So we know for every data point, we know what level S2 cell that is a part of. And once we have this view, we're going to call this one telemetry data 1 hour bin is the name of it. And then we can use that telemetry data 1 hour bin in here. So first thing we want to do, we saw something like this before, we're going to use the geopolygon to S2 cells. So what this does is this creates the array of S2 cells that will just cover my polygon. So I assume I've already got a polygon defined, and I'm going to pass that into it, and I'm going to pass in level 15, and now I'll get an array of S2 cells that will completely cover the polygon and maybe a little bit more. It'll be the minimum number of cells that can cover that polygon. And then we can use that array. Well, first of all, we're going to take advantage of the fact that we've pre-aggregated S2 cells and recalculate S2 cells in this materialized view. And because that pre-aggregation has a column called S215, then we can use this as part of our query to say, and S215, the S2 cells level 15 for each data point, see if they are in this array. And so now we're filtering the picture I showed you earlier. We're filtering by only those data points that are in these S2 cells that just cover, they're just a little bit bigger than our polygon. And now when we do our table scan, this will run much, much faster. So we'll store that in a variable called devices in S2 box. That variable is going to actually be a table in memory. And now we can query this devices in S2 boxes. And now that's when we're going to run our table scan. That'll be a lot faster. So here's some optimization tips. Think about if you find yourself querying the same and aggregating the same data over and over again, think about creating a materialized view to do that ahead of time. Time filters, ADX is optimized for time series data. So if you can filter on time first before you filter anything else, that'll go a lot faster. You'll be able to take advantage of the indexes inside of ADX. There aren't a whole lot of built-in indexes ADX because it wants it to run a lot faster and handle lots and lots of data. Filtering on calculated columns, generally that will slow you down because you're almost certainly going to have to do a table scan. Of course, the way you get around that is pre-calculating those. And then I didn't talk about this much, but case-insensitive operators are faster than case-sensitive operators. There's a link down at the bottom here with more best practices if you want to learn more. All right, let's show a demo using KQL. In this demo, I'm going to show you how to do some KQL queries inside of an ADX database. So here's the cluster I created before. If I go down to databases, select the database that I created, and if I click on query right here, in here, I can run a bunch of queries here. So for example, remember we had a customers table. If I just type customers right here with nothing else and click run, I see a list of all of those customers. But I can also I'll do this pipe, and the pipe says the output of the customers will be the input of the next thing, and that'll be a filter. And you notice check out the IntelliSense that pops up here. It knows that where is an option, so I'll do that. And I want to do where year-to-date sales. See, the IntelliSense again knows what columns are in this table is greater than or equal to 100,000 right there. And if I run that, then I get only a subset of those, only those with 100,000 or more in year-to-date sales. Let's do the same thing except now we'll do order by instead. Order by postal code. And I want to specify, if I don't specify anything, it'll go in descending order, which is a little counterintuitive to me because I'm used to SQL Server, which by default will sort them in ascending order. I like to make sure that I always explicitly say ascending or descending. I don't want it to be obvious to anybody reading this code. So I want to first sort by postal code and then by last order date, and how about in descending order? Right here, I'll run that, and you can see it's all the rows here, but they're posted first by postal code, where the 60605 is on top and 98109 is on bottom. And if there's a tie, which there is right here for these three rows, then I want it by last order date in descending order. So there we go. January 4 at 13 o'clock, same day at 11:30, and January 2nd. All right. And then let's do order by about year to date sales in descending order. That shows them all in descending order, but I only want the top three. So what I can do is pipe take three. So I want just these three, Scott, Bill, and Jeff, right there, because they are the ones with the highest year-to-date sales. Might be useful information when you're trying to follow up with customers. All right, let's do something else. The project, how about this? We'll do all the rows, but we only want to project 2 columns right here, and that's good. We can also do calculated columns. Let me add to this. The next day is the last order date plus 1 day. And then the year-to-date sales, and then the remaining quota is $2 million minus year-to-date sales. Our goal is to sell $2 million to everybody. We want to know what's left of that. So we've got a couple of calculated columns in here. Now, it might make sense. Maybe you want to do a calculation. See, we've done a calculation on year-to-date sales. What if we want to do a calculation on a calculated column? Can we do that? Let's give it a try. We'll add in here, comma, expected sales equals remaining quota times 2. So let's try that. Click run, and it doesn't work. We can't do this because this is running essentially the same time as that. However, there is a way to do that. Let me get rid of it from here. I'll use the extend keyword. So I need to pipe. So the output of this, which includes remaining quota, will be the input of this extend. And now I have a calculated column under extend, and this will work. So now whatever the twice of this is just 2 times that. And that could be useful. You could do it with not just regular math, but also with date math as well. Last order date plus 1 day, run that. And next day is here. Things like that. All right, let's do an aggregation. How about this? Summarize, count the total number of customers and their average year-to-date sales by postal code. And you can see, well, I don't have the column on here, but there are a bunch of different postal codes. Let's do just the customers here so you can see the postal codes. There's a couple of them in 95014, a few of them there, and a couple of them in 898052. So let's aggregate by postal code. Run that. And now for each postal code, run that again. For each postal code, we say there's 3 in that, 3 in that. There's the average year-to-date sales, only 1 in each of these. So that's how you do aggregation in code, in KQL. Now you would be looking at this and thinking, wow, this is a lot to learn. Even with the IntelliSense, there's a lot to learn. I know SQL, so I can read it, but it's kind of hard for me to write it. Well, here's something really nice. Imagine if you know SQL and you would say, boy, I know this query right here. That's a SQL query that if I had the same table structure, I could do this. How would I write that in KQL? Well, this is really cool. You type explain, and once I type explain, then I get the output is the query in KQL. I just think that is so cool, and I can now run this. This is a great learning tool if you're familiar with SQL, but you're not really familiar with KQL. It happens there's not any data in there, but it's worth looking at. All right, let's take a look at some time series data. I created the table called drone data. If I want to see all the rows, I just type drone data right here. There's 26 rows you can see up here. And let's do just something simple with that. Order by timestamp, project out the drone ID, the timestamp, the longitude, latitude, the battery life, and the previous life. And this is really interesting here. So now I've got a calculated column that says battery life, previous battery life. It's because I'm sorting by timestamp. It is the battery life of the record before this. And now that I have this, I can use that in a calculated column under extend to say the battery life change is the difference between the battery life and the previously battery life, which I calculated. That would be pretty hard to do in SQL, but here it's very simple. So here's my battery life right here, 100, 99, 98, 97, etc. And here is the previous one. So this 100 reflects that. This 99.9 reflects that. This 99.8 reflects that. It's always the previous one. And that makes it really simple for me to calculate the current battery life minus the previous battery to see that, oh, it looks like it's going down about 0.1 each time. And now here's I probably should just filter this by drone ID, but that's the idea here. This one, it went down by 0 and then by 0.1, and then it didn't change, and 0.1, 0.2, etc. So we can see a delta of, for each record, how much the battery life is decreasing. Pretty cool query, simple to do in KQL. Let's do this. Let's try this summarize by bin right here. In this case, we're looking at the drone data, and we want to summarize by bin 1 hour. You notice the data is not every hour. It looks like it's about every 15 minutes. We're getting it here. We only want to get 1 row per hour, and we want to go take the maximum timestamp within that hour and output the drone ID, the longitude, the latitude, and the battery life record for that, whichever row has the maximum timestamp. Run this. You see there's a lot fewer rows here, 1 per hour, and you can see if there's one at 10:45. Now there wasn't one right on the hour, so here it is. I'm sorry, timestamp. Timestamp is 10, 11 o'clock, 12 o'clock, 13 o'clock, and 14 o'clock. And there wasn't always something right on the hour, so it took something close to it. All right, what else do we want to do here? Oh, let's do something with these geographic functions here. Let's do this one right here. So for drone ID 1, we want to order by drone ID and timestamp. That makes sense. And then we project these 3 columns, drone ID, timestamp, longitude, latitude. And then we're going to calculate the distance between the current row and the previous row. So the previous row, longitude, and the previous latitude, we're going to pass those 4 values into this function, geo distance 2 points. So when I run that, here we go. At this time, I was at negative 73 and 40. And then here I'm at negative 73.97 and 40.73. So I moved by longitude, but not by latitude. And what I'm doing is I'm calculating the difference between this point and this point. And that's what's right here. This is what's calculated between the longitude, latitude of the current row and the longitude, latitude of the previous row right here. Pass those 4 values into geopoint by distance, and it will calculate the distance between this one and the row before it. Of course, it's blank for the first row because there is no previous row. But now we get an idea of how far it is traveling for each one of these things. All right, let's do something a bit more complex. We're going to work with polygons here. So in this case, I showed this code on a slide. This is a 4-sided polygon right here. I define some latitude, longitude for the 4 corners of it. And then I define these points, P1, 2, 3, 4. Those are the corners. And then I use this pack function to actually create a polygon right here. So I had to look in the documentation to see how to do this. But once I did that, now I can use this geo point in polygon. I could say for every point in the drone data table, tell me whether or not it is in the polygon. And I'm going to filter on that. If it's in the polygon, I only want to see those ones that are in this polygon above. And I'll sort by drone ID and timestamp. All right, let's go ahead and do that. Run that, and there were only 4 points in that polygon, 1 for drone 2, 3 for drone 1. There's the longitude and latitude of each one, and then also happens to show the battery life at that time, which may or may not be significant to me. What else do we have here? How about, let's do the geopoint to S2 cells, just to illustrate this function here. So I'm going to do it. Take this geopoint to S2 cell, pass in a longitude and latitude, and I want it to be at level 13 right here. I can't remember exactly how far that is, but it's about halfway down between 0 and 30. So it's a moderate sized rectangle. And I'm only doing it for drone ID 1. So right here, so all I've done is just added this extra column here, S2 13, and you can see that some of these, like these 2 happen to be in the same S2 cell. These two are right here. Here's 1, 2, 3, 4, 5. There's a bunch of them here that are in the same S2 cell. So it just gives you an idea of proximity for each of the cells. If they're in the same S2 cell, then we know that they're close to each other. All right, and how do we do that? Or how do we use that? This is what the query I had on my slide, code to create a polygon, and here we go. I'm going to put everything, convert the for this polygon and level 12. I want to know an array of S2 cells that will cover that polygon, the minimum array of S2 cells that will cover that polygon right there. And I'll store that in S2 arrays. And then I will create a variable called drones in S2 boxes. This is a table or table variable, in which case I'll query the drone data. And I want to know, first of all, this query right here, geo points to S2 cells, convert everything to an S2 cell at level 12, store that as S212, and then I'm going to filter on that, say I only show me the ones that are in this array, where the S212 is in this array of S2 cells that just covers the polygons, a little bit bigger than the polygon. Now, once I have that and I store it in this variable, now I've got a small subset of the total number of data points. And if I query that smaller subset, I'm still doing a table scan, but I'm scanning much fewer of those when I say where geopoint in polygon for every longitude, latitude, tell me yes or no, is it in the polygon? Only filter on those that are inside of that polygon. So if I run this whole query right here, I get these 4 right here. Same thing as I got before, but it should run a lot faster, particularly if I have an enormous data set of the results are only a small subset of that. All right, got a few more things I want to show you here. How about materialized view? Here's how you create a materialized view. Right here is the .create async materialized view. I say backfill equals true because I want to include everything that's already in the table in my view. If not, it'll be empty until I start adding new rows. It's on a table customers, and the query is going to be customers. I'm going to summarize the count, the minimum year-to-date sales, the maximum year-to-date sales, the average year-to-date sales, and I'll summarize them by postal code. So run that. It creates a materialized view. And now if I want to query that, I just say my material. What did I call it? I'll just copy that and paste it right here. And there are all the rows in this materialized view. They were pre-populated for me. So that can be a big advantage if this happens to be a very large thing that requires enormous calculations. And I can work with this just as if I were working with a table. I can say pipe where year, what is it? How about average sales is greater than 100,000. How about that right here? And work with it just exactly as if I were working with a regular table here. If I want to change the materialized view, there is a command called .alter materialized view. We give the name of the view on table customers, and we specify how we're going to change it. So in this case, we're going to change it. We're just going to remove, we have the num max sales, average sales, and we're going to remove the min sales. We don't care about that anymore. So we want to modify it here, do that, and now if I query it again, you'll see it just has 1 fewer columns than it used to. All right, functions. Let's create a function. Nice simple function in this case. I've got a doc string that's just some documentation about it. I can put it into a folder called samples just to order that. Here's the parameters, revenue and expenses. They're both decimals, and then it's going to return revenue, my expenses. I'll click on run right here, and that looks pretty good. So let's if I expand this, by the way, you can see not only do I see my tables here, and I see my materialized view, and I see my functions, but because I said I want this in a folder called samples, it actually organized that for me right here. And then I can use that function like this, query the customers and extend profit equals profit. That's this function out here, and just pass in the year-to-date sales, comma, year-to-date expenses. It'll return the difference between those two. Right here, there's my profit. It's really just 40,000 minus 10,000 equals 30,000. 750,000 minus 650,000 is 100,000. So I'm using that. That's a scalar function. In other words, it just returns a single value. I can also create tabular functions. Those will actually return a table of data. Let me do that right here. I know I'm going fast, but I'm going to share all this with you at the end. Create or alter a function. There's my doc string documentation. There's my folder. It's called drone route, and it takes a start date time, an end date time, and a time bin length, which has a default. If I don't pass that in, it'll assume 1 hour, and then it's just going to use those input parameters as query parameter here, where timestamp is between start and end time, and when it does the summarize by bin, instead of hard coding a value in here, it takes this parameter right here, which will default to 1 hour if we don't pass it in, and that's what we're going to do. So this should return a table of data. Let me run that here, and just to show that, the way we call it is with the name of the function, drone route, right here, and pass in the parameters. Here there are 3 parameters: start date time, end date time, and bin length. There's the start date time 11 o'clock, end date time 13 o'clock, and bin length is 30 minutes. So if I run that, I get 1 row every 30 minutes. If I don't pass in this last parameter and run it, it'll assume 1 hour, and I get 1 row per hour. Okay, those are my demos for using KQL. Let's quickly head back to the slides. Let's go back to the slides. I really just want to share some links with you. Actually, all you really need is this first one, tinyurl.com/Giard ADX slides, because that contains this slide deck, which of course contains this slide, which contains all these other links. But I'll describe the links to you. There's the official documentation right here for Azure Data Explorer and for KQL. Right here are a bunch of articles and videos that I created. There's tutorials to get you started and up and running using ADX and KQL. You can see a list of them over here on the right. There are some videos of some case studies for our ADX customers, and then I actually recorded the interview with the ADX product team that they have some interesting things to say if you want to see from their perspective. That's all I have for today. Thanks so much for your time. Have a great day.